Good morning. I hope you had a good weekend. We're going to continue talking about what happens when you disturb an equilibrium. And at the end of Friday, we left off talking about a butane to isobutane equilibrium with a K of 2.50. And remember, as long as K is greater than 1, that means you have more product around than you have reactant. And so at equilibrium, there was 1.25 molar of the iso and 0.50 molar of the regular butane. This divided by that, products divided by reactants, confirms that you're at 2.50. And this graph right here shows the slope of 2.5. So at the slope of 2.5, that means that the iso to butane ratio will be this 2.5 ratio, and any point along here you can do it. But anyway, why this problem's a little different is we're going to quote-unquote disturb the equilibrium. And what that means is we're going to add in a lot of the reactant, the butane. So instead of having only 0.50 moles per liter butane, now you have a total of 2.00 molar of the butane. And the question is, what's going to be the new equilibrium concentrations? Now, on Friday, we talked about Le Chatelier's principle. And if you add a lot of a reactant, how do you expect this equilibrium will adjust to accommodate that? You think you'll have more products, more reactants, or no change? More products, that's right. As you add something, the reaction shifts to the side away from what you added. So if you add a reactant, it would shift to the product side, to the right. If you added a product, like more isobutane, you would expect the reactant to shift to the left, away from what you added. So anyway, we can use this information to calculate the new equilibrium concentration.
Butane and isobutane can interconvert to reach a dynamic equilibrium. The graph shows the equilibrium line. If we add butane to the system, the equilibrium is disturbed, and the butane reacts to form isobutane until the equilibrium is reestablished.
Cool. So this just shows, this lighter blue line shows what happens as we add the extra reactant. And so instead now of being on this nice slope of 2.5, i.e. at equilibrium line, now we're way over here to the right. And these equilibrium systems wish to adjust themselves back to the equilibrium position. So the little bit darker blue line shows it going back to the equilibrium slope. And our goal basically is to tell what these new numbers are. And of course on a graph you could read it, but you can also calculate it using Q. So Q comes in really handy because it's a way to predict how the reaction should shift. And Q is just products over reactants. It looks just like K. And the Q value here is 0.625. So Q 0.625 is smaller than K 2.50. And this is another way to confirm what Le Chatelier's principle has said. This number, and when it's settled, if you will be equal to 2.5. Obviously, you're not there yet. So in order for this number to become like this, you either have to make the numerator, the top, bigger, and or make the bottom denominator smaller. So that means you're going to have more products, less reactants. The reaction will shift to the right. So notice here how we use Le Chatelier's principle and the Q versus K to both compare and confirm that more products will be made. You can use the ICE table to figure out what the new concentrations will be. Initially, you have butane from the two sources, what was there initially and what we added, and the isobutane stays at 1.25. Now, because Q was less than K, we are going to have a shift to the product side, and that means this one will go up, this one will go down. And another way to figure out which one is plus X and minus X is because by Le Chatelier's, you add a reactant, the reaction should shift to the products. Shifting to the products means the plus X will go there, and you can't have something from nothing, so if this is plus X, this one would be minus X. Anyway, at equilibrium, 2 minus X for the butane, and 1.25 plus X for the products. You can set these equal to 2.5. 2.5 times 2 minus x, if you multiply both sides by 2 minus x, will equal 1.25 plus x. When you solve for x, get the x's on one side and the numbers on the other, x 1.07. So you can calculate the new values. All right, 2 minus 1.07 will be the butane, that's the 0.93. And 1.25 plus 1.07 will be the 2.32. So the equilibrium has definitely shifted to the products. Why I like this problem is because it does show a use of Q, all right, to predict how the reaction is going to change. And also it shows how Le Chatelier's principle, although not like an analytical tool per se, it does help you to predict what things are going to change. So if you don't like comparing Q and K, you can use Le Chatelier's. On the other hand, you don't like using Le Chatelier's, Q and K would be another way to see what's going on. So Le Chatelier's principle is kind of important, and we'll talk about it off and on as a way to kind of make sense of our answers. So this is just kind of an overview of the Le Chatelier's principle stuff. If you change the temperature, then you need to know if the reaction is endothermic or exothermic. And from there, you can predict the changes. The difference when you change the temperature is that you're actually changing the value of K. So like on the last example with butane and isobutane, K was 2.50. If you had a change based on temperature, that would change maybe the 2.5 to 3.5 or something like that. It would actually change the number. So K will change with temperature. The K that you are figuring out in lab from last week that's due this week, that K is only good at room temperature. You start changing that and you'll see changes. Catalysts don't change the K, they just make the reaction go to equilibrium faster. So if you're the impatient chemist, and I raised my hand there definitely. Anyway, if you are, or you just don't want to wait, catalysts can make the reaction go faster. So reactions that would take a long time will go faster. You don't actually change the K, but you do make them both come to equilibrium faster. And then finally, the one we'll probably use the most is when you add or remove a reactant or a product. And if you add something, the reaction shifts in the opposite direction of what you added. So we added a reactant earlier, and the reaction shifted to the product side. If we added a product, it would shift to the reactant side, the opposite of what you added. On the other hand, if you take away something, then the reaction shifts to the side that you took something away from. So you start taking away reactant, reaction will shift to the reactant side. Or if you take away the product, reaction will shift to the product side. Any questions on that? So that's the end of this chapter. A lot of you have seen these kind of things before, but I just want to point out, at the end of the chapter I have little advertisements for things that might be helpful. In your companion, you have both study guides and concept guides. And a study guide is a bulleted list of the things that I feel are kind of important from the chapters. And you might go over those just to make sure that they kind of make sense, that you know what's happening. Concept guides are worked problems from the different chapters. So it'll show examples of how to calculate an equilibrium constant, stuff like that. I'm also throwing up here the types of equilibrium constants handout. We're going to see lots of different types of K coming up. In this chapter, we saw K sub C, which was the equilibrium based on molarity. We also saw K sub P, which is the equilibrium based on pressures. We'll see some different ones next chapter. This is just a list of all the ones, I think, that we're going to see this quarter. So if you forget what a KP is, because we won't use it a lot, you can look back at the list and kind of see what's happening. So, cool. Cool. All right. So let's move on. And now get back to something that chemistry is really known for, and yet we haven't really done justice to. We haven't talked about it that much. And it's the chemistry of acids and bases. And we're going to spend quite a bit of time, now that we know what equilibrium is all about, to talk about acids and bases. If you were with me in Chem 221 or in another class, we talked briefly about acids and bases, and acids create H+ ions, bases basically have hydroxides. And very quickly in Chem 221, we talked about the pH scale. pH is a way to quickly see if something is acidic or basic. And as a quick reminder, the pH scale usually goes from 0 to 14, not all the time, but usually. 7 is considered neutral, where you don't have an excess of acid or base. But if you hear a pH that's less than 7, those are considered acidic, and pHs larger than 7 are considered basic. There's a correlation with the concentration of the acid. That's what that little part is, and we'll talk about that in this chapter. But if nothing else, look at this little silly picture here. Almost everything around us has a pH component. Everything you drink and you eat and you clean with and stuff, all these things have some kind of a pH. And your knowledge of the pH will really help you to see like which ones are good. The things that people eat, tomatoes, oranges, okay, fine, meats, all right, as a vegetarian, I hesitantly say that, but profit back on. Anyway, those kind of things that we eat are usually acidic, all right? Most of what we consume and eat are acidic things. And then if you look at the other things here, like cleaners and stuff, those are usually going to be basic. So we'll see some kind of things, and this has just some other examples of different things and stuff that you might see. So anyway, we'll talk about all this. We'll go back into what pH is, what an acid is and stuff. Let's check this out. Oh, finally, I'm splitting this into 2 sections, all right? This section's gonna be on what acids and bases are like by themselves. So you have a flask of an acid, we can analyze it. You have a flask of a base, we can analyze it. The next section will be what happens when acids and bases are mixed together, all right? So this chapter mostly will be on talking about acid and base properties, how to define if something's acid or base and stuff. And then the next section, we'll see what happens when the acids and bases come together. Now, as a quick review, acids and bases can be split into strong and weak sections, all right? And the strong ones are the ones that are more exciting usually, but we'll see that the weak ones have some really interesting properties as well. Strong acids, what that means is they dissociate 100% into some type of hydronium ion, which is what H3O plus is, and in this case nitric. So nitric acid, one of the strongest acids out there. Nitric acid reacts with water, it makes hydronium and nitrate. And notice here, we're back to using the good old one-directional arrows in this case. After going through equilibrium, this one with a strong acid will always write just a single arrow. And it's assumed that all of the reactants go to products. And this one definitely pretty strong.
When a few drops of water are added to solid calcium hydride, a violent reaction occurs that produces hydrogen gas.
The strong acids and the strong bases are the fun ones to show videos on, all right? Because they pew pew, you know, they explode and stuff, and they make lots of cool things. And anyway, so acids and bases, very overtly strong and weak, and we'll see how that works. But again, this part I want you to realize here is that the acids, they do need water for our purposes to react, and hydronium, which is H3O plus, is going to be a big player in what an acid is.
When nitric acid, HNO3, encounters a water molecule, it forms an acidic solution by donating a proton, the H plus ion, to the water to form a hydronium ion and a nitrate ion.
Not all hydrogens are acidic, all right? But in this case, the H on the HNO3 is readily given off to water. Nitrate is a very stable polyatomic ion. It's very water soluble, it's good to go. And hydronium is formed when the nitric acid comes in. So I would argue as a chemist that the action of a nitric acid really comes from the hydronium that's being formed. It is so product favored that it's just gotta happen. Here's another example with HCl. HCl also reacts with water. Chloride, very happy by itself, sticking around, and hydronium is made. Now, in the real world, there are literally hundreds of thousands of acids. Almost all of them are weak acids. So one thing that's really helpful in this class is to know/memorize the 5 strong acids. If you see another acid in Chem 223 that's not one of these, and I don't state this as another strong acid, then you'll assume that it's weak, and that will be important. So nitric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid, and perchloric acid are the 5 commonly held strong monoprotic acids. Monoprotic means they have one acidic H+, and we'll focus mostly on things that create just one H+. So if later on I say, hey Hunter, I've got some blah, blah acid, and he has no idea what blah, blah is, he can go back to this list, and blah, blah is not one of these 5 strong acids. He can assume it's weak, and that will be kind of important for us later on. Okay. Now, weak acids are quite different than the strong acids. In a strong acid, 1 mole of HCl makes 1 mole of hydronium, and we use the single-sided arrow. Very, very common weak acid is acetic acid. Acetic acid is essentially the active ingredient in vinegar. When you have a weak acid, equilibrium plays a huge part of it. So notice here in this reaction, acetic acid is reacting with water, and it does make that hydronium, but it's in equilibrium, all right? And so what that means is that not all of the acetic acid makes hydronium. In acetic acid's case, it's roughly 1 in 10,000 molecules or so of acetic acid that actually make hydronium. Most of acetic acid stays at acetic acid. You don't have as much hydronium running on. We're going to use acetic acid quite often in this class as an example. And so just realize that a lot of times, for whatever reason, lazy chemists, whatever version you want to use, instead of writing CH3CO2H all the time, a lot of times people will write HOAC for acetic acid. And the part that comes off of acetic acid, this part without the H+, is the acetate ion, another common polyatomic ion we've talked about off and on. If you see OAC-, that's another way to show that that's the acetate ion. This is the structure of acetic acid. It's got sp3 carbon there, an sp2 carbon right there, and an OH right there. These hydrogens are not really acidic, all right? They don't dissociate. It's this one right here that will fall off. When you have a negative charge on this oxygen, resonance makes that negative charge stabilized. Resonance means you can make the lone pair electrons move around. You can make a double bond and have a negative charge right there. This is just review stuff from Chem 222. If it's all wah, 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 then just ignore me. I'm kind of being silly chemist here. Anyway, prop that back on. Summarize. Weak acids, you don't use single arrows, use equilibrium, all right? It always means that you're gonna have more reactant than you have product. But again, hydronium will be an active player. Hydronium is what makes an acid an acid. Now, bases are kind of the opposite of acids in many different ways, and this is kind of a cool thing we'll talk about. And you can have a strong base and you can have a weak base, just like you can have a strong acid or a weak acid. Sodium hydroxide is a very, very common strong base, and we've used it in lab. And again, what that means for us is that this thing in water breaks up into sodium ions and hydroxide ions. Hydroxide is the hallmark of a base. So if hydronium is what acids create, hydroxide is what bases will make. There are only 3 strong monobasic bases that you have to know about. Again, monobasic just means that they give off 1 hydroxide, all right? And those 3 are sodium hydroxide, potassium hydroxide, lithium hydroxide. So again, Justin and I are in the lab, and I say, hey, Justin, go grab me some strontium hydroxide. All right, strontium hydroxide, not on that list. All right, that either means A, I didn't tell you about it, or B, more likely it's a weak base. This is an example of a dibasic system. If you have two hydroxides, then that can be one way that you have a strong system. Now, calcium hydroxide is a strong base, but it's not one that you need to worry about. We're going to focus mostly on the mono systems, like one acid, one base, but it's not a hard extension to do this kind of stuff. Calcium hydroxide is a very common, strong dibasic system. We'll talk more about the dibasic and diacidic things later, but just realize there might be more. But again, for your purposes, NaOH, KOH, and LiOH, those are the three players. And there are weak bases. So just like weak acids make hydronium, but not as much as strong acids, weak bases make hydroxide, but not as much as the strong bases. And one of the most common of the weak bases is ammonia. Ammonia is NH3. And when NH3 is placed in water, you'll see that it makes hydroxide.
Ammonia acts as a base in solution by accepting a proton from a water molecule. This liberates a hydroxide ion and results in a basic solution.
So again, ammonia doesn't have any OH on it, so it doesn't look like a sodium hydroxide base or a lithium hydroxide base. But what ammonia does is it does pull one of the H pluses off of water to make ammonium. And in the process, then, hydroxide is created. So anything that creates hydroxide, we can consider a base at this point. Ammonia is a base. But it's a weak base. We're using equilibrium, all right? This K is much less than 1, we'll see. And so that means that, one of every roughly 10,000 ammonias will break down to hydroxide, but most of it stays as NH3. This is the Lewis structure for NH3. You can see it's tetrahedral. It's got the lone pair on it, trigonal pyramid, all that kind of stuff. But again, the exciting part, relatively speaking, the exciting part is that hydroxide is formed weak base. Now, there were several acid-base theories thrown around for a long time. There are 3 acid-base theories working around. One of them is called Arrhenius, and we're not going to worry about that one because it's kind of old school. But the main acid-base theory was created simultaneously in 2 different labs by these people named Bronsted and Lowry. And Lowry kind of kept his notes, didn't publish, and I think scientists like writing the O with the circle line through it, whatever. So most of the time this theory is just called the Bronsted acid-base theory. Technically it's Bronsted-Lowry, sorry Lowry, but Bronsted is the one that's usually referred to. And in the Bronsted theory, acids donate H plus ions and bases accept H plus ions. Now, hydronium, H3O+, is a source of H plus ions. So you can also substitute in for H plus, H3O+. They're kind of used interchangeably in this section. So classically, if you think about it, acids are giving up H pluses and the bases are accepting H plus. But you can also think about it from hydronium, which is a little weird. So Bronsted theory is the main theory we're going to use in this chapter. We are going to look at the Lewis acid-base theory at the end of the chapter, but the Bronsted one is the main one we're going to focus on. So. Cool. If you have ammonia, all right, and ammonia is reacting with water, all right, ammonia is basically taking the H plus from the water, all right? So that means that ammonia is acting as a base. It's taking that H plus. On the other hand, though, water is giving the H plus to the ammonia. So water itself is acting like an acid here. So in the Bronsted-Lowry theory, all right, the acids are giving up H plus, like water gives up H plus to ammonia, and the bases are taking the H plus. So NH3 becomes NH4. And thinking about what an acid base is kind of cool.
Ammonia acts as a base in solution by accepting a proton from a water molecule. This liberates a hydroxide ion and results in a basic solution.
So notice here, if you look on the reactant side, ammonia is taking an H+. If it's accepting an H+, it's a base. Water is giving up an H+, so water here is acting as an acid. And the products of this reaction, like we saw, are ammonium and hydroxide. So going left to right, you can clearly see that NH3 is the base and water is the acid. But this is an equilibrium, all right? And products don't usually stay as products when it comes to equilibrium. The products will end up making reactants. So if you think about it from the product side going to the reactant side, something really interesting happens. Ammonium here is giving up an H+ to hydroxide. So ammonium is acting like an acid. And the hydroxide, OH-, is taking the H+ from the ammonium. The hydroxide here is forming a base. So notice here that acid and base theory, you can look at it from both directions. Reactants going to products and products going to reactants. And if I can really blow your mind one more time, ammonia, a base, creates ammonium, an acid. And water, an acid, creates hydroxide, a base. And in the opposite direction, you can see the base makes an acid and the acid makes the base. There's a symbol in Chinese and stuff thing, and I'm drawing it horribly, but it's the yin-yang symbol, and like one side is black, one side is white, and there's a little white dot there and a black dot there. This is perfect for acid and base theory, because if you think about it on the left side, base and acid react to make acid and base, and then those new acids and bases react to make the opposite acids and bases. It's like they go back and forth and back and forth. And by no means am I pushing any of this kind of stuff on you. I just find it really interesting that this ancient symbol somehow represents a lot of things that are happening in acid-base equilibrium, which we'll see more of, so. Now, here's ammonia and water making ammonium and hydroxide. Notice how ammonia and ammonium are related by an H+. The NH3 takes an H+ to make NH4. The NH4+ gives up an H+ to make NH3. We call these conjugate pairs. And a conjugate pair is always two chemicals related by addition or subtraction of an H+. So add an H+ to ammonium, you make ammonium. Take away an H+, you make ammonia. So those are conjugates. And you can probably see that water and hydroxide are conjugates as well. Give up an H+ to make hydroxide, take an H+ to make water. So we have two conjugate pairs here. Conjugates are just related by an H+, like give or take. Every acid has a conjugate base. Every base has a conjugate acid, and it kind of goes back and forth, which again is why I like this yin-yang symbol so much. So, any questions? Okay. Here's another example of an acid-base reaction. This reaction has hydrogen carbonate, sometimes called bicarbonate, although I don't really like it, but anyway, what am I going to do? Hydrogen carbonate reacts with water. It makes hydronium and the carbonate ion. So if you look here at the conjugates, remember conjugates are related by an H+. So take away an H+ from this one and you make carbonate. Add an H+ to carbonate, you've got hydrogen carbonate. And the same thing here for water. If you add an H+ to water, it makes hydronium. And hydronium here, you take away an H+, it makes a base. Acids have more hydrogen than bases. So if you're not clear which one is the acid and the base, and we'll see there's good reasons for that, acids have more H's. So there's 3 H's there, 2 H's there, this is the acid. No H's, 1 H, this will be the acid, etc., etc. Now, I know you're all burning to ask this question and you're just being polite and shy, and I totally dig it. However, on the last slide, water was acting like the acid. It was reacting with ammonia, all right, to make ammonium and hydroxide. Here, water is acting like a base. It's reacting with an acid to make carbonate and hydronium. Water is playing both sides of the fence here a little bit, and we'll talk about that in a little bit. But first, which one of these combinations do you think is not an acid-base conjugate pair? If you have a conjugate system, it's a relationship with just an H+. One of them will have one extra H+, and the other one will be deficient. All right? So we're looking here for the combination which is not an acid-base conjugate pair. HNO3 and NO3- are conjugates. You add an H+ to NO3, you make HNO3. You take away the H+, you make NO3. And of course, this one has more hydrogen, so it'll be the acid, and this one will be the base. And all of these are conjugates, except if you look at this first one, there's an oxygen there, and there's no oxygen on that side. The only thing that the acid-base conjugates will have different is the H+. So A would not be a conjugate pair. Like taking away an H+ here, you'd have ClO-, and adding an H+ here, you'd have HCl. So they're not the same on both sides. Any questions? Okay. Let's talk a little bit more about water.
Without the addition of any other substances, two water molecules can interact with each other to produce a hydronium ion and a hydroxide ion by transfer of a proton from one water molecule to another. This process is called autoionization.
Oh my God, Maria, don't drink your water. This is something sometimes jerky chemistry instructors will say, so I apologize to Maria. The reason I bring this up as a joke, though, is because water naturally has some acid and some base in it. And if this was like hydrochloric acid, I would absolutely take the thing out of your hand. Don't drink it, man. On the other hand, water, you can see, does have some acid. Now, if you remember from Chem 222, water, we're showing the molecular geometry here, and it's bent. But there are lone pairs kind of sticking out right there. And water undergoes hydrogen bonding, which is a really strong part of the molecular forces. So what happens is one of the H+ can be absorbed by a hydronium, and we'll talk more about how that all happens later. But it's easy in water to have some hydronium, the hallmark of acids form, and some base in the process form, OH-. And all the time, every drink of water you've ever had, you will have some acid and base. Now, I jokingly say that to Maria about not drinking the water because all of us drink this all the time. It's something our bodies have naturally grown accustomed to. But it is kind of interesting to think, you know, there's a lot of fear and scare around acids and bases, and really every time you take a drink, and it can be coffee too, by the way, man. Oh, I love it, caffeine. Anyway, it can be any substance and stuff that you drink. Water always has some acid and some base in it. They call this autoionization. Water is not the only substance that this undergoes, but is by far the most common, and is one of the more powerful ones too. Scientists have studied autoionization in great detail, and at 25 degrees Celsius, which is about room temperature, an equilibrium constant has been determined. Now, the reaction is two waters making hydroxide plus hydronium. So Kw, a very special kind of K, is going to equal hydronium times hydroxide, but there's no water in the denominator. Why is water probably not included in the denominator? Liquid, that's right. Liquids and solids are not included in the equilibrium expressions. So when scientists have studied this at room temperature, Kw 10 to the minus 14th. So does that value of Kw imply we're going to have more hydronium and hydroxide or more water? Water, totally. K less than 1, and this number is quite a bit less than 1. K less than 1, you're going to have more water this side than you're going to have the products, hydronium and hydroxide. So when you drink water, when all of us drink water, there is a little bit of hydronium and hydroxide, but by far there's more just regular neutral water. If you're curious how much acid and how much base are in water, you can actually figure it out. Because two water molecules, when they dissociate, they make one hydroxide and one hydronium. So the amount of hydronium and hydroxide in neutral water will be the same. So Kw, which equals hydronium times hydroxide, you can think about it as hydronium squared or hydroxide squared because the values are the same. If you take the square root of Kw, you're going to get this number, 1.00 times 10 to the minus 7th moles per liter. That number is the concentration of hydronium and hydroxide. Is this a big concentration or a small concentration? Small. Like in lab, a lot of times we had like 10 to the minus 3 and stuff. When you did the equilibrium constant lab, some of the FeSCNs were 10 to the minus 5. This is even smaller than those. So when you're drinking water, chug a lug, all right, because there's not that much acid and base in there. It's very small, and again, our bodies are used to it. Another interesting thing, though, is that acids and bases can coexist naturally together if they're at small concentrations. And 10 to the minus 7th here represents an amount where the hydronium and the hydroxide will be the same. We're going to see that this Kw is the foundation of a lot of the things we're going to do in this chapter. And knowing Kw, 10 to the minus 14th, is really important. And also in the back of your mind, I want you to remember that the things we're going to talk about this chapter are all based around room temperature. If any of you go into research in medicine, where the human body is certainly not room temperature, it's like 37 degrees Celsius, some of the things we talked about may have to be tweaked a little bit. K changes with temperature, and having the human body's temperature versus room temperature, sometimes you will see subtle little differences.
So we should be memorizing the top number and not the 10 to the negative 7?
That's right. We'll see, Jay, that this number plays into a lot. Now, this 7 right there is related to pH of 7, and so you'll see that come back. But this is the big one right here, the 10 to the minus 14th. Good. Other questions? That was a good question. Yes?
What does the W stand for?
Water. It's the water autoionization. That's a good question too, you bet, that's right. There are other compounds that do this, Jessica. This is the equilibrium for water's autoionization, I guess. It's the WAC. No, I'm just joking, I don't know. Yeah, that's a good one. All right, here's another question. We have a solution that has a hydronium of 10 to the minus 8th moles per liter, all right? And if you want to define the hydroxide value, what you can do is you can go back to Kw. And Kw, 10 to the minus 14th works fine. It's 1.00 to the minus 14th. That equals hydronium times hydroxide. So in a solution with a hydronium of 10 to the minus 8th, you can put 10 to the minus 8th in right there, and you can essentially then solve for X, solve for the hydroxide. If you do this in your calculator, 10 to the minus 14th divided by the 10 to the minus 8th, it comes out to be 10 to the minus 6. So in this case, it's a nice way to use this Kw to find out hydroxide if you have hydronium. And of course, you can reverse that too. You can find hydronium if you have hydroxide. And again, as long as you're at room temperature, 25 degrees Celsius, Kw is awesome. But again, if you go into medicine, you may have to tweak some of these things a little bit because Kw might change. So let's say that now we're going to put some sodium hydroxide in water, all right? 0.0010 moles. That's not a lot of sodium hydroxide. Sodium hydroxide is roughly 40 grams per mole, so that number times 40 is still pretty small. However, we can use this information to calculate, the hydronium and the hydroxide. Now, is NaOH, first of all, is it an acid or a base? Base, that's right. If you have an overt source of hydroxide, like in sodium hydroxide, that means this is going to be basic. I'd also like you to know if sodium hydroxide is a strong base or a weak base. Which one is it? Strong, that's right. There's only 3 strong bases, NaOH, LiOH, and KOH. So for our purposes, this is going to be a base. Now a base means you're going to have more hydroxide than you have hydronium. So at the end of the day in this calculation, the hydroxide concentration should be larger than the hydronium concentration. So those are things to think about, like before I start these kind of problems. Now, in all of these kind of calculations, when you're dealing with K, it's moles per liter. So the first thing to do is to think about what the molarity is. Oh, and here's another thing too. Le Chatelier's principle is actually really useful in these kind of circumstances too. As we add hydroxide to this solution, all right, we start with just water and hydroxide. We add hydroxide and some of this reaction will shift to the left. So what that means is we're going to have a ton of hydroxide. We're not going to have a lot of hydronium. Adding hydroxide means this reaction goes to the left. And while hydronium and hydroxide were both 10 to the minus 7th moles per liter, the number that Jade asked about earlier, our new number for hydronium should be a lot less than that because we're using it up as the hydroxide comes in. So for these kind of problems, what I would do is again set up some kind of an ice table. All of the sodium hydroxide ends up as hydroxide. That's what a strong base means. If it was a strong acid, then all of the strong acid would end up as H3O+. So in this problem, the hydroxide starts 0.0010 moles per liter. So moles divided by liters gives you this much. And we're not going to assume that there's any hydronium to begin with, because 10 to the minus 7th is such a small amount. Now, if water is breaking up into these guys, then both of these will increase. Without the hydroxide, it was 10 to the minus 7th. But with the amount of hydroxide here, we expect there to be a smaller number here for X. So X is still going to be made because you can't have it equal to 0. This number plus X will be the amount of hydroxide. Kw equals hydroxide times hydronium, or X times 0.0010 plus X. Now, Kw, 10 to the minus 14th, equals X times 0.010 plus X. Technically, this is a quadratic expression. You would have x squared plus 0.0010x minus 10 to the minus 14th equals 0. And if you have the solve button on your calculators, you can absolutely put this in. But one thing that helps is that x before the hydroxide was in was 10 to the minus 7th. What would be roughly the value of 10 to the minus 3 plus 10 to the minus 7th? A relatively big number relative to a relatively small number. It would be just this 10 to the minus 3. That's right. 10 to the minus 3 is many powers of 10 larger than 10 to the minus 7th. So if x was 10 to the minus 7th, the pure water value, this plus this would still be this number. Remember sig figs, when you add and subtract, you have to cut it off at the largest doubtful digits? In this problem, that's this number. And 10 to the minus 7th would be 1, 2, 3, 4, 5, 6. It would be many digits over to the right. So sig figs, cursed thing since chem, whatever class you started with, I know, actually help us here, because instead of having to go through the quadratic, we can just assume that this x is really, really small. And if you do that, the math becomes much easier. Kw equals x times 0.0010. You divide both sides by 0.0010. You end up then with the value of hydronium. So you can see here what we're doing. We're pulling this little x out, because 10 to the minus 7th plus 10 to the minus 3 is still basically 10 to the minus 3 when it comes to sig figs. So if you solve for the new hydronium, Kw divided by 10 to the minus 3, 10 to the minus 11th moles per liter. We predicted that adding a base would make the reaction shift to the left. So what was 10 to the minus 7th is now 10 to the minus 11th. That's a pretty good shift to the left. This guy is basically equal to itself because it's so much larger than what would have been 10 to the minus 11. Any questions? Yes, yes, Lindy.
Can we still do it the regular way?
Yes. It will take you more time, John, but you can, absolutely, man. I'm trying to not only show you the map, but I'm also trying to give you some kind of ways to get around some of it. Even if you put, solve, you put the equation in /x, it's gonna take longer than 10 to the minus 14 divided by 10 to the minus 3, but you bet you can do it totally. Oh, good, yeah, that's cool. So yeah, those of you that are in love with your calculators, that's awesome, keep going, but this is just a faster way. I really have your back. You may not believe me all the time, but I prop that back on. Other questions? I was going to say something. Oh, what this problem is kind of good for, all right, is that the Kw, that 10 to the minus 14, is basically always going to equal hydronium times hydroxide. And if you have one value, like here you have hydroxide, you can readily find hydronium. Alternatively, if you had just hydronium, you can then quickly find hydroxide using Kw. So this is just the first of many ways we're going to use this Kw to figure out how much acid and base is present. All right. So, hydronium, 10 to the minus 11th, hydroxide, 10 to the minus 3. If you wanted to call this solution acidic or basic, all right, acidic just means you have more hydronium, and basic means you have more hydroxide. And a 10 to the minus 3 hydroxide is a lot bigger than 10 to the minus 11. So we would call this solution basic, all right? 10 to the minus 3 hydronium is larger than 10 to the minus 11. And this is one way to find out how acidic or basic something is. But it's really messy to say 10 to the minus this, 10 to the minus that. So the next thing we're going to talk about is how we can use, nice 80s graphics there, but anyway, how we can use pH, all right, as a quick way to find out if something is basic or acidic. And this guy, who also has the O's with the slash through his name, was the person who created the P scale, all right, the pH scale in lots of different ways. And what Sorensen did, pH equals minus log hydronium. Now this has to be the base 10 log, the LOG, not the LN. Don't use the LN unless you know what you're doing. So pH equals minus log of hydronium. We saw earlier, the one that Jade asked about, that hydronium and hydroxide were both equal to the 10 to the minus 7th number. If in your calculators, if you go minus log of 10 to the minus 7th, you get a pH value of 7. So neutrality is where hydronium and hydroxide are equal to each other. pH of 7 is that number. It assumes you're at room temperature because we're still using Kw, that's where the 10 to the minus 7th came from. But if you're at room temperature, then pH of 7 should be good. If the hydronium was 10 to the minus 11th, which we saw, pH minus log of that number, pH 11.00. So again, pH is less than 7, greater than 7, excuse me. This would be a basic solution. So instead of comparing the hydroxide to the hydronium and saying that 10 to the minus 3 was larger than 10 to the minus 11, pH is a really nice way. It's always based around the hydronium, so as long as you have the hydronium, you can quickly find it. If your pHs are larger than 7, they're basic. If they're less than 7, they're acidic. And unfortunately, Public Enemy doesn't know anything about acids and bases. Yeah, boy. Base, how low can you go? Oh, come on, man. Base is how high can you go? It totally bums me out. I love Public Enemy and stuff. #1. So Chuck D had an MBA, which is an awesome degree, definitely. Took a lot of college and stuff, but he obviously didn't understand acids and bases, because it should be bases, how high can you go, not low. All right, please don't drop that. Anyway, have a good day. We'll talk about this more.